Hi everyone. This presentation was supposed to be part of a conference, but we ran into some technical difficulties, so I'm re-recording it from now. The title is From Ancient Remedies to Modern Contraptions, Tracing the Evolution of Biocompatible Materials, and it's a sort of summary on my research. First of all, let me speak again about my new laboratory. The Biomaterials Engineering Laboratory will open on the 1st of April of 2024. We will focus on modeling, production and characterization of materials that are applied in biomedical field, in particular polymeric and composite materials. Well, doing this job I often wonder what is the most accurate definition of a biomaterial, and I selected three that I will present to you now. One is from about 50 years ago, and it was given at the 6th Annual International Biomaterials Symposium of 1974. And it says that a biomaterial is a systematically, pharmacologically inert substance designed for implantation within or incorporation with a living system. Well, it's interesting that it speaks only about pharmacologically inert substances, while in 1969, Professor Hench, which you can see a picture here, developed bioglass, and bioglass is for sure not a pharmacologically inert substance, but is designed for implantation. So this definition was already outdated at the time. About 10 years later, we have a new definition that speaks of a substance or combination of substances, synthetic or natural in origin, which can be used for any period of time as a whole or as a part of a system which treats, augments or replaces any tissue, organ or function of the body. Well, this is very general. It speaks about both synthetic and natural origins, and it speaks about treating and repairing and replacing tissues and organs, so to repristinate, to make the body whole, functional again. And the last one, which I believe is probably also the current one, is that any substance or combination of substances which can be used for any period of time again, but the focus is on maintaining or improving the quality of life of the individual. So we are shifting from a definition that is focused on material science. We are going more and more into medicine, and even in medicine we are shifting on the feeling on the quality of life of the individual, which is a little difficult to quantify in the proper way. But if we have a look at this article, which was written by David Williams in 2014, the title is "There is no such a thing as a biocompatible material," which is sort of controversial. And this Professor Williams, at the time, he was the editor-in-chief on Biomaterials, which is the most important journal on biomaterial science. And his idea was that biomaterials by themselves don't make any sense. We cannot measure biocompatibility. There's no general way to measure biocompatibility. We need to consider the system, and the system is the material and the surrounding environment together. So to speak about something, a material by itself as a biocompatible, is misleading at best, and I agree with this, and I will show you why. As you know, I like human history, and if we go back almost 5,000 years, we find this is the oldest prosthetic device ever retrieved, and it's an artificial eye which was used in Iran more than 4,000 years ago. It was put inside the eye socket in substitution of the original eye. It was made of bitumen, which is absolutely not biocompatible because it's a mess of different ingredients. It can also release a lot of harmful substances, and it was protected by a layer of gold. And we know that it worked because in the surrounding of the prosthetic eye there is some white deposits, and these white deposits are caused by the contact of this implant with the inside of the eye socket. little forward, we see this skull retrieval that has some strange thing in the middle of the forehead, and that round mark is a piece of a nut shell. So basically, this skull had a defect. The defect was closed using a piece of wood, basically, and the wood was not rejected. Actually, the natural bone of this individual was able to grow inside the wood, and they became like fused together as one material, even if we know perfectly that wood is not a good biomaterial, because it's something living. There's going to be allergic reactions, there can be parasites inside, bacteria, especially at that time. So it's incredible that this experiment was successful at the time. It's the only experiment of this type that we were able to retrieve. Moving a little forward, we have this, which is probably one of the most famous artificial implant of all times. These are pieces of seashell that were implanted inside the bone of the jaw, and again the surrounding bone was able to bond with this material. This is not surprising by itself, because shells are made more than 90% of calcium carbonate, but it depends on the type of shell. But there's a lot of calcium carbonate inside, and calcium carbonate can be dissolved by the osteoclasts, so it can be remodeled. The materials can be used again to create bone. So it's not surprising that it can be destroyed and built again as bone. What is surprising is that, again, like wood, this can have a lot of parasites. It still has proteins inside that can cause adverse reaction, and for modern standards, in this condition, it will definitely not be considered a biocompatible material. Moving a little bit forward again, we have this artificial teeth retrieved from a Gallo-Roman necropolis, and these teeth are in a terrible condition. But the surprising thing is the one made of iron, which was implanted inside the bone, probably. And we now know that most iron-based alloys are not very biocompatible. As you can see, it is rusted, so it was not a good candidate for an implant at the time. Of course, they didn't know. Now there are modern like special stainless steels that can be used for implants, because they're very resistant to biological environments, or there are also alloys that can be destroyed by the human bodies by bioresorbable iron alloys. But in this case, this was absolutely not something that could be considered biocompatible, but still it probably was used, and that's why we retrieve it in this condition. Jumping again, this is a very famous denture. These are the dentures of George Washington, one of the many, because he started losing his teeth when he was very young. And these, well, the teeth by themselves are probably biocompatible. There's not much to speak about them, but the metal surrounding it is lead, so we know that it's poisonous, it's harmful, and it can cause a lot of damages. But since it's very moldable, very easy to shape, it was used to obtain these prosthetic devices that actually work very well. And if we jump again to the 70s of the last century, we find finally a polymer which is considered to be, at the time was considered to be the most promising, the strongest polymers of all time, which is PTFE, also known as Teflon. And it was used to make acetabular caps like the one that you cannot see, because these are X-rays and the polymer cannot be seen by X-rays, but you can see the femoral head and the stem that go inside the pelvis. This is a hip prosthesis. Well, this is one debris that came out from this kind of hip prosthesis made with Teflon, and this is the prosthetic implant itself. As you can see, This is exactly the same of the X-ray, by the way. You can see that there is it has been cut, the cap has been cut. You can see the head, you can see that there is like a sort of hole on the top of the head, and this is because the position of the head shifted. Look at the two X-rays, more than 1 centimeter up, because by just friction between the metal and the polymer, the PTFE was removed. These small debris of PTFE were able to fly around in the surrounding tissue, and more than 2 years after implantation there were inflammations and what was called at the time infection, but it's not properly an infection, causing the failure of the implants about 2 years after implantation, which is surprising. It was considered to be one of the first cases of human-made diseases. Something similar happens also for materials that are still in use. In this prosthetic device, the head is made of an alloy which is based on cobalt, chromium, and molybdenum. But the shape is a little different, by something that looks like this, and this also can form debris, and this debris can lead to the formation of what is called pseudotumor, or also to bone resorption, so the bone is destroyed, which also leads to the loosening of the implant, so the implant can literally detach from the bone. This also happens in the titanium alloys. I will show you an example. You see here 2 examples of hip implants made of titanium, and there are places in which this titanium is in contact with something else, either titanium in the upper example or ceramic material in the lower example, and this type of connections can move a little bit, which causes what is called fretting, which is a type of wear. And this type of wear in an aggressive biological environment can result in damages that sometimes are just a little change of color when the oxide is not so thick, and sometimes is a devastating failure in only 2 years, and as you can see in the component on the right, it completely broke down. There are many possible reasons for that: the pH, the formation of wear debris, the composition of the synovial fluid, the inflammation, biological reaction, etc., etc., etc. But the point is, titanium usually behaves well. In this case, in the right case, it was a disaster, and we are not sure what happened. So can we call titanium biocompatible? It's just like the cobalt chrome before. We have something that in standard conditions is perfect, then something happens and it's not perfect anymore, and it's not biocompatible anymore. But if these exceptions exist, are the materials really biocompatible? And now we'll move to something that we know is not biocompatible, which is silver nanoparticles. Silver nanoparticles basically are the mixture of 2 of the worst things that you can put inside the human body. One is silver. Silver is very aggressive, is cytotoxic, it can kill the human cells it touches. Nanoparticles also, depending on the size, they can enter the membrane, they can enter the nucleus of the cells, and they can destroy the material inside the nucleus of the cell, which basically is what we call cytotoxicity. And we did this experiment with particles of silver with various size, and like everyone knows actually from the types of Paracelsus, I think, is depending on the quantity, on the size of the nanoparticles, on the quantity basically of the nanoparticles, the cytotoxicity can be there or not. And in our test, it takes quite a lot of nanoparticles, even in the smaller size, to actually see toxicity. So this is silver nanoparticle to be considered biocompatible if the amount is not so much, if the size is big enough. You see, it's a sort of flexible definition. We cannot say that one material is completely biocompatible or completely not biocompatible. There are lots of different conditions that we need to take care about. And we can also see something interesting in aluminum. As you probably know, aluminum is considered to be a dangerous material that can bioaccumulate and can cause a lot of different troubles. Maybe you don't know which troubles, but there are many biological effects that can be caused by aluminum. But if we do a standard test like this cellular culture in a liquid that contains different amounts of aluminum, we actually see that both the fibroblasts and the osteoblasts, which are two different types of cells, are still, well, in a healthy condition. They even proliferate more in presence of aluminum ions when compared to the controls. Well, actually, when compared to the lowest amount of particles. But the interesting point is that this is because we are looking at the wrong thing. Here we are looking at about on the number of cells, but aluminum does something completely different. If we take the second batch, the osteoblasts, which are the cells that build the bone, and we have a look at the quality of this bone, we see that the amount of bone that is produced decreases with the increase of the amount of aluminum. So the presence of aluminum does not affect the proliferation, the number of cells, but the cells become unable to produce bone. And the little bone they produce, well, it's a little difficult to understand on the graph on the right, but if you see the peaks at about 950 centimeters minus 1 in the left graph, you see that it disappears at 100 ppm. Well, that is the mineral part of bone. Basically, the small amount of bone that is produced in presence of aluminum does not contain enough mineral. It's mainly made of collagen tissue, soft tissue, so it's even not really bone. So aluminum is doing some damages that by just checking the number of cells, which is a typical test for biocompatibility, by just checking that, we cannot see how dangerous aluminum is. But if we look at what happens, the metabolic reactions of the cells, we see that it is dangerous because the bone there is not in healthy condition, it cannot be formed, the little that is formed is damaged. And then we come to my most recent research topic, which is on silicon nitride. Silicon nitride is a ceramic material which is used in a lot of applications like load-bearing applications, cutting tools and things like this, because it's hard and it's very stable. But if you put it in water, especially in something more aggressive like the biological environment, what happens is that the outside layer of silicon nitride gets oxidized, and by catching the oxygen, it releases nitrogen, which forms ammonia or ammonium ion, and this ammonia and ammonium ion are dispersed in the surrounding environment. So we have an exchange, oxygen enters in the silicon nitride, and nitrogen goes out of the silicon nitride, so the surface is oxidized and releases ammonia. What does this ammonia do? Well, to the cells, not much, but the bacteria, which are a little less resistant to ammonia, can actually be inhibited or even killed by these ammonium ions. So it's a sort of weak antibacterial material. On the other hand, on the cells, it proved to be more or less comparable with aluminum oxide. Well, depends on the composition, depends on many things, but it is not extremely bioactive, but it also doesn't look to be very dangerous on the macroscopic scale. Because as we go a little bit more in deep on the action of silicon nitride, we notice something peculiar, something special. In the image, in the gray image you see on the left, this is piece of silicon nitride, we grow bone on the silicon nitride, and then we remove the bone. You can see that there's a sort of thick layer surrounding it, covering this spot, the area around this spot. What you see in the center of the image is actually the silicon nitride. What is surrounding is supposed to be bone, but when we go and check the composition of this bone, there is almost no calcium, so it's mainly collagen again. Why? Well, because even if the amount of ammonia is not so much to be extremely dangerous for the cells, it's still something that the cells don't like. And what they do is they try to isolate the source of ammonia ion. So they build this protective layer, this shell of collagen, and after, on the top of this collagen, they will then start the normal activity and build the bone. But the first layer which is formed is a relatively thick layer of tissue which has no minerals inside. Titanium alloys also are coated by a thin similar layer when they are applied in vivo. Silicon nitride is covered by a thick layer which is not bone. It's not technically bone, it's a protective layer, an insulator. And if you don't believe that this is enough, if we look at the image on the right, in this image I mixed two different powders. One is yttrium oxide. You can see the areas of yttrium oxide are marked in red. One is silicon nitride, and we put this in a culture media containing the osteoblasts, the same cells that produce bone that I already spoke about before, and they only produce bone on the blue areas, on the silicon nitride. There is no bone, only produce bone on the red areas, on the yttrium oxide area. There's no bone on the silicon nitride. This is because if they have the chance, they avoid the silicon nitride and they prefer working on other materials, in this case yttrium oxide. So does this mean that silicon nitride is not a biomaterial? Well, again, depends on the definition. Here I prepare a list of some of the tests that are done to assess biocompatibility. You can imagine that we cannot do all these tests all the time, and it also depends a lot on the patient. I mean, the condition of the patient, the age of the patient, other problems that may happen during the life of the patient, etc., etc. Conditions are complex, so biocompatibility cannot be guessed in advance. Well, can be guessed, but it cannot be 100% safe. It cannot be 100% sure. Also, it depends a lot on the application, because as we've seen before, a little bit of nanoparticles of silver will not do anything bad to you, but if we increase the amount, then it gets dangerous. And this is again because the idea that biocompatibility can be measured is completely wrong, and this is something that scientists in my field do all of the time. We just want to do a standard test and say that the material can be used in biomedical applications, but this is a huge misunderstanding. This is not biocompatibility. Biocompatibility cannot be measured. It is a property of a system which is composed of an environment, a biological environment, and a component with its own shape, etc., which is made of a specific material. Only considering all the system we can actually say that something is biocompatible or not. So it's sort of complex. What I do recommend, especially to young researchers and PhD students, is to consider that their material is just half, is just one piece of the puzzle. The other piece of the puzzle is the actual application, depends on the application, is the biological environment. So we should speak about biocompatible systems and not about biocompatible materials. materials that are biocompatible in some applications are probably not biocompatible in other applications. I give you another examples. The amalgams that you have in your mouth are biocompatible in the mouth, but I would not trust them in other locations. For example, in the hip, where there can be fretting, and then mercury can actually leach out of the prosthetic implant. And the other thing to consider is that even if we measure biocompatibility somehow in the laboratory using any test that we want, that is one point in time or a few points in time, but the time variable changes a lot. For example, we use to fix prostheses, sometimes we use a special glue which is made of a polymer called polymethyl methacrylate. This polymer is put between the bone and the prosthetic implant, and it glues together the bone and the prosthetic implant, and we think it's biocompatible. But I actually did testing on these pieces of this polymethyl methacrylate 20 or even 30 years old, and their chemistry was completely changed, their color was changed, and they smelled like ammonia because, well, something happened inside. They absorbed a lot of biological molecules, and basically they were not polymethyl methacrylate anymore. They were absolutely not biocompatible anymore, but still they were inside the body. So biocompatible systems are complex and changing, and when we do our research we need to keep in mind that this will happen. And like I write in this slide, and we need to address the elephant in the room. We cannot say that something is biocompatible because we did some testing in the laboratory. We can say that it can be biocompatible in some specific applications, and considering some time frame, some time window for that application. And this is what Professor Williams was saying. Biocompatibility is not a property which is related only to the material. Well, thank you for your time.